Today we're going to walk through the main topics for Week 1 in statistics and connect them to situations you already deal with as a college student and in everyday life. This course is not about memorizing formulas or doing long calculations by hand. It's about learning how to think about data so you can judge claims, make informed decisions, and understand information you see in classes, at work, and in the media. You already encounter statistics all the time. Course evaluations, GPAs, placement scores, social media polls, product reviews, and news headlines all use data to make a point. This course gives you tools to decide whether those numbers are meaningful, misleading, or missing important context. We'll start with parameters and statistics. Anytime you see a number describing a group, the first question to ask is who is included. A population is the entire group you want information about. A sample is only part of that group. A parameter describes the population, meaning everyone in the group was included. A statistic describes a sample, meaning only some people were included. A simple rule to remember is this: whole group equals parameter, part of the group equals statistic. For example, if a college says the average GPA of all graduating seniors this year is 3.1, that is likely a parameter because the school has records for every graduate. Now compare that to a statement like, 60% of college students prefer online classes. There are millions of college students, so that number must come from a sample. That makes it a statistic. Sometimes statements sound official but are still statistics. For example, students at this college spend an average of 3 hours a week studying. Unless every student was tracked, that number still comes from a sample. This distinction matters because statistics are often used to influence opinions and decisions, and understanding where the data come from helps you decide how confident you should be. Next, let's talk about how we describe data using numbers. Measures of central tendency tell us what is typical in a data set. The three most common measures are the mean, the median, and the mode. Choosing which one to use affects the story the data tell. The mean is the average. You find it by adding all the values and dividing by how many values there are. The mean is familiar and widely used, but it can be strongly affected by extreme values. For example, if one person earns far more money than everyone else, the mean income may not represent what most people actually earn. The median is the middle value when the data are listed from smallest to largest. If there is an odd number of values, the median is the single middle number. If there is an even number of values, the median is the average of the two middle values. The median is often used for income, home prices, and salaries because it better represents a typical experience when data are skewed. The mode is the value that occurs most often. Some data sets have one mode, more than one mode, or no mode at all. The mode is especially useful for categorical data, such as the most common major, shoe size, or survey response. The range gives a quick idea of spread. It is the largest value minus the smallest value. While it's easy to calculate, it only uses two values, so it doesn't tell the whole story about variability. Software like StatCrunch will calculate these values for you. Your responsibility is to choose the most appropriate measure and explain what it tells you about the data. Now let's talk about data shape. One common shape is the normal distribution. A normal distribution looks like a symmetric bell. When data are normal, most values are near the center, and extreme values are rare. In a normal distribution, the mean and the median are the same. Heights, standardized test scores, and measurement errors often look approximately normal. Many real-world data sets are not normal. They are skewed. A helpful rule is this: the tail points in the direction of the skew. Right-skewed data have a long tail to the right. This is common with income, wait times, hospital stays, and time spent studying. In right-skewed data, the mean is greater than the median because high values pull the mean to the right. Left-skewed data have a long tail to the left. This might happen with scores on an easy exam, where most students score high and only a few score low. In left-skewed data, the mean is less than the median. Understanding skew helps you choose the right summary statistics and avoid misleading conclusions. Another important idea is standard deviation. You will calculate standard deviation using StatCrunch, not by hand. Standard deviation tells you the typical distance of values from the mean. A small standard deviation means most values are close to the average. A large standard deviation means values are spread out. For example, two classes might both have an average exam score of 80. If one class has a standard deviation of 2, most students scored close to 80. If the other class has a standard deviation of 15, scores vary widely. Standard deviation helps describe consistency, not just performance. Standard deviation is always 0 or positive, and uses the same units as the data. In roughly normal data, values more than about 2 standard deviations from the mean are relatively uncommon. Before we move on, there are 2 important ideas to introduce that will help you interpret results correctly. First is correlation versus causation. Just because 2 things are related does not mean one causes the other. For example, if students who attend tutoring have higher grades, that does not automatically mean tutoring causes higher grades. It may be that more motivated students choose tutoring. Statistics can show relationships, but they do not automatically prove cause and effect. Related to this is the difference between observational studies and experiments. In an observational study, you observe what already exists, such as surveys or school records. In an experiment, you actively assign a treatment, such as testing 2 different study strategies. Experiments are stronger for supporting cause and effect conclusions. Now let's move on to sampling. Sampling is used whenever collecting data from everyone is too expensive, too slow, or impossible. Medical studies, election polling, marketing surveys, and college research projects all rely on samples. The key goal is representativeness. A representative sample looks like the population in important ways. A simple random sample gives every individual an equal chance of being selected. This helps reduce bias but requires access to a full list of the population. A stratified sample divides the population into groups based on a characteristic such as department, age group, or class year. A random sample is then taken from each group. A helpful memory trick is that stratified sampling means some people from every group. This method is used when representation from all groups is important. A cluster sample also divides the population into groups, but instead of selecting people from every group, entire groups are randomly selected. Everyone in the selected groups is included. Cluster sampling means all people from some groups. This method is often used because it is more practical or less expensive. A systematic sample starts with a random starting point, and then selects every nth individual. This method can work well, but it can be risky if there is a pattern in the list. A convenience sample uses people who are easy to reach, such as friends, classmates, coworkers, or social media contacts. Convenience samples are common in student projects. They are not wrong, but they limit how far you can generalize your results. When you use convenience sampling, you must explain who you sampled and how that might affect your conclusions. Next, let's talk briefly about data types, because this explains which graphs to use. Categorical data place individuals into groups, such as major, gender categories, or yes or no responses. Numerical data represent counts or measurements, such as test scores, hours studied, or age. Bar graphs are used for categorical data. They answer the question, how do categories compare? The bars are separated because the categories are distinct. Histograms are used for numerical data grouped into intervals. The bars touch because the data are continuous. Histograms help answer the question, what does the distribution look like? Stem and leaf plots and dot plots are useful for small numerical datasets. They help you see individual values, clusters, and outliers quickly. Outliers deserve special attention. An outlier is a value that is far from the rest of the data. Sometimes outliers represent real but unusual cases. Other times, they come from data entry errors, such as typing 500 instead of 50. A good habit is to always look at your graphs before interpreting results to catch impossible or suspicious values. Throughout this course, StatCrunch or any statistical software can handle the calculations and graph creation. Your workflow will usually involve entering or uploading data, creating graphs, viewing summary statistics, and then writing a few sentences explaining what you see. StatCrunch gives you the numbers and graphs. You provide the interpretation, the context, and the explanation.